Let's consider this example. We need to solve this system, and to solve this, let's try to find eigenvalues and eigenvectors of the given matrix A. So if this one is the matrix A, we as usual find the determinant of the difference A minus Ri and make it to be 0, and you can check that in this case you will have three roots, and two of them are 3, and the third root is minus 3. So we are not here in the case when we have 3 distinct eigenvalues, since we have the same eigenvalues. So what should we do in this case? What can we do in this case? Let's consider A minus 3i applied to vector u. So let's try to find the eigenvector corresponding to this eigenvalue 3 and make it equal to 0. So let's see what we have in this case. A minus 3i is the matrix. 1 minus 3 is minus 2, minus 2, 2, minus 2. 1 minus 3 is minus 2, 2, and 2, 2, and minus 2. Apply to vector u. Let's say vector u has coordinates x, y, z, and this must be equal to 0. And you can notice here that all 3 lines of this matrix will give us the same equation, just one equation, minus 2x minus 2y plus 2z equals to 0. So this system gives us only one equation, and so since there are 3 unknowns, we have to introduce 2 parameters here. So let's first maybe divide it by 2 to make it simpler. So this is minus x minus y plus z is 0, and from this we can find that z is x plus y. So let's introduce 2 parameters. Let's say x is s and y is, let's say, t. And in this case, the solution of the system x of t, sorry, it's not solution yet, this is eigenvector, is x is s, y is t, and x plus y is s plus t. So we can split it into s times 1, 0, 1 plus t times 0, 1, 1. So you can see that there are 2 parameters and 2 vectors here, and you can check that these 2 vectors are linearly independent. So these 2 vectors are linearly independent. So you see we have 2 eigenvalues, the same 3, and for these 2 eigenvalues we get 2 eigenvectors in fact. So we can take u1 to be s1, 0, 1, so in the case when t equals 0, right? And u2 is a vector t, 0, 1, 1. So we get for 2 eigenvalues, which are basically the same, we get 2 linearly independent eigenvectors. Okay, let's just find the eigenvector for the third eigenvalue. So a minus, so in this case plus 3i, u is 0. This is the same as a plus 3i will be 4 minus 2, 2, minus 2, 4, 2, 2, 2, 4, apply to x, y, z is 0. And in this case the vector will be, so what do we have here? The 3 must be linearly dependent, so we can choose just two of the lines to write 2 equations, minus 2x plus 4i plus 2z is 0. And the third one can be obtained from these two. You can easily see this. You just sum them, you get the third line, right? So the third line is unnecessary here. Okay, let's try to solve it. What do we get? Let's divide by 2 first to make this simpler. Minus x plus 2y plus z is 0. And from this we can, let's say, take difference between these two equations. In this case, this z will be cancelled, and we get 2x minus x, we get 3x. Minus y minus 2, we get minus 3y is 0. So it means that x equal to y. And 2x minus x plus z is 0. So x plus z is 0. So z is minus x, right? So we can write the eigenvector corresponding to the third eigenvalue. Let's take x to be s, then y is also s, and z is minus s. So the third eigenvector, the third family of eigenvectors is this family here. So what we get overall for two eigenvectors, we get two family of eigenvalues. Let me just see what it was. So 1, 0, 1 and 0, 1, 1. And for the third eigenvalue, we get this family of eigenvectors. So how we write the solution? The solution we write in the same way as before. So this will be c1 e to the 3t, and the first eigenvector 1, 0, 1 plus c2 e to the 3t. The second eigenvector 0, 1, 1 plus c3 e to the minus 3t, corresponding to this eigenvector 1, 1, minus 1. So this is solution of the system. So, and sometimes for repeated eigenvalues, as in previous example, we can find linearly independent eigenvectors. So sometimes if we have repeated eigenvalues, we can still find linearly independent eigenvectors, which will help us to write down the general solution. But the crucial word here is sometimes, so it's not always like this. And this can be done for symmetric matrices. So in previous example, the matrix was 1 minus 2 2 minus 2 1 2 2 2 1. So this matrix is symmetric. So you see, if we draw line along the main diagonal, you see that the entries are symmetric with respect to main diagonal. In fact, the definition of symmetric matrix is when A is the same as A transpose. So you transpose the matrix, you get the same thing. In this case, we call the matrix to be symmetric. So if matrix is not symmetric, then it's not always possible to find linearly independent eigenvectors. So for non-symmetric matrices, there can be the case that it is not possible to find linearly independent eigenvectors for repeated eigenvalues. Let's see an example. For example, let's consider the matrix A, which is 1, minus 1, 4, minus 3. And if we try to find the eigenvalues, Ri, which is the determinant y minus r minus 1, 4, minus 3 minus r equals 0, we get that two eigenvalues are minus 1. But try to find eigenvectors. So A minus R, so R is minus 1, so A plus I applied to U is A plus I, so this will be 2, minus 1, 4, minus 2, applied to U some vector with two coordinates, must be 0. So you see the lines are linearly dependent, so we can use just only one equation. So y equal to x. So it means that u is, if we take, let's say, s to be x, then y will be 2s. So this is s, 1, 2. So eigenvector, all eigenvectors are only in this form. So there are no two linearly independent eigenvectors. So what can we do in this case? We will discuss in some following lectures. But let's summarize now what can we do. So the first thing, if n times n matrix A has n distinct eigenvalues, say R1 and so on, Rn, then you can find n linearly independent eigenvectors u1 and so on un, and write general solution of the system x prime is ax in the form x is c1 e to the r1t u1 plus so on cn e to the rnt un. And secondly, if there are repeated eigenvalues, of A and A is symmetric, then it is still possible to find n linearly independent eigenvectors u1 and so on un, and write the general solution in the same form. So in this form here.